Let's try another example problem. We have a 1 meter long rope that's stretched between two posts, and you hang a weight of 4.9 newtons right in the center of the rope, and it sags, which we all would expect to have happen, unless it was like a steel wire. And you're being asked what's the tension force on each side of the weight. And you're being asked what is the tension force on each side of the weight. So let's start with our free body diagram. And here's our weight. And we know that F of G is equal to 4.9 newtons. We also know that there are two ropes, or two parts of the same rope. And you might notice that these are starting to look pretty similar. Yes, the general idea of tension force problems, they're all going to look fairly similar, but you still need to draw them every time because you need to have all that information organized. Now some of you might want to start putting this information into your free body diagram. The problem is a free body diagram is about forces, and those are not forces. We can still break our tension force into X and Y. We have Ft to X and Ft to Y. Ft1X and Ft1Y, but you can see we don't have an angle. While I know that my drawing is not symmetrical looking, it's supposed to be, so we do know that Ft1 is equal to Ft2, but we need to do something to find these angles. If you're picturing this visually, which I always recommend try to picture the situation in your head, you could see, hopefully, that you might be able to use these distances, because sagging would be over here and the length would be up here. You could use those to find the angle. So I'll just sketch one little part of it. And we're not going to label these as Ft and Ftx and Y because this is not forces. We're just picturing the wire or the string, and that's where the weight's hanging down. If the whole rope is a meter long and we're hanging the weight exactly in the center, then there should be 0.5 meters on each side of the weight. And if the rope sags down 0.2 meters, this should be meters. You can draw a triangle for a situation, and you can usually draw several different ones as long as you're consistent. Our free body diagram has forces. This little triangle we're sketching over here has lengths or distances. And we want to know what this theta is. This is opposite and this is hypotenuse, so we're going to use SO. The sine of theta equals opposite over hypotenuse, and you can see the meters would cancel out. And we can calculate that our theta is 23.6 degrees. You can see that you're going to need two significant figures at the end, so I'm going to round everything to have three significant figures in the middle, so that I know that I'm not going to round away information I need. And because these are the same situations, we know that this is also 23.6 degrees and this is 23.6 degrees. So now we can go back and start talking about equilibrium. Because the weight is hanging motionless, the sum of the forces in the x direction is equal to 0. This means that our two x components equal each other, which we knew anyways because we knew that the two triangles were the same. In the y direction, we know the sum of the forces in the y direction is equal to 0, which means that this force, this 4.9, has to counteract these two forces. We can say Fg has to equal 2 Fty's. 4.9 is equal to FTYs. So our FTY has to equal 2.45 newtons. And you can see after we found the angle, it looked just like the first example. Really, once you have your free body diagram with your gravity and the angle of the triangles, they're all going to look pretty similar. I can add my FTY up here to my free body diagram, or I can sketch another triangle near the bottom if you like. Because that is opposite, we're going to use sine again. The sine of theta equals opposite over hypotenuse. And if we round our tension force to two significant figures, we can calculate that it's equal to 6.0 newtons.